Okay, so hello everyone. I am Srishi Siddharth. I am a PhD student associated with the Systems and Control Group at IIT Bombay, and I'm also the TA for this course, EE90. So let's start the tutorial session for the second week. Alright, so let's recall what we did in this week. We had two canonical forms. The diagonal form and the Jordan normal form. So to compute these two canonical forms, we relied upon the partial expansion. So it's and then we also looked at some questions of the other two forms. So controllable canonical form and observable canonical form. Alright, so let's first start with a quick review of the partial fraction expansion. Alright, so let's just consider transfer function f. It's some numerator and denominator, and this is expressed as some gain k times s plus the first 0, second 0, all up to n zeros. So we're saying it's an nth order system. So let's say this is some m which is less than n. So this implies that it's a strictly proper transfer function. And then we have the poles in the denominator. So s plus p1, s plus p2, all up to s plus pn. So the partial fraction expansion for distinct poles we have that f of s can be written as some constant. So let's name the constant as c1 upon s plus p1 plus c2 upon s plus p2 all up to cn upon s plus pn. Alright, so this is the case when we have distinct poles or distinct eigenvalues. So eigenvalues of the system are the poles of the characteristic equation or the denominator of the transfer function. So in the case of distinct poles, you have this. And how do you find the constant c1, c2 up to cn? So for example, you need to compute c1. You just consider this expression and evaluate this at minus of p1. So let's see. Okay. So you have a transfer function f of s. So I'm just going to write this down. S plus 3 upon s plus 1, s plus 2. So this is strictly proper. It has distinct poles or eigenvalues. So now let's look at the partial fraction expansion. C1 upon S1 plus 1, C2 upon S plus 2. This is nothing but. So to compute C1, we have S plus 3 over S plus 1, S plus 2 times S plus 1. So this evaluated at S equals minus 1, we get 2. Similarly, you can find out what C2 is. So let's do this quickly. It's going to be S plus 3 upon S plus 1 evaluated at S equals minus 2. So this is the partial fraction expansion. So f of s can be written as 2 upon s plus 1 minus 1 upon s plus 2. Okay. Now let's move on to a case when the transfer function is not strictly proper. So let's see. This is case 1. And let's see case 2. So case. Alright. For case 2, m is equal to n. So let's take an example. The transfer function is s cube plus 5s square plus 9s plus 7 upon s plus 1 s plus 2. So for this case it is greater than. Okay, so let's just expand the denominator first. So it's s square plus 3s plus 2. Okay, so we need to convert this to a strictly proper transfer function. Okay, so what we can do is just divide. So just a second. Let's start from. We have s cube plus 5s square plus 9s plus 7. We have s, so it's s cube plus 3s squared. We have 2s squared plus 9s plus 7 plus 2. This is 2s squared plus 5s plus 4. And we get 4s plus 3. Let's see if this is correct. So this is minus. Yeah. So if s can actually be written as s plus 2 plus 4s plus 3 over s square plus 3s plus 2. Let's check once. Alright, so it's s cube plus 3s square plus 2s plus 2s square plus 6s plus 4. Okay, we have additional terms plus the denominator. This is s cube We have 5s square. Then we have 12s. Alright, so this is incorrect. And we have plus 3. Okay, plus 7. So you have s square plus 3s plus 2. So let's check here. So we have s times this. Then we have 2s square plus 9s plus 7. Okay, then we have 2s square. Sorry, this was 6s. And we have 3. So this is, I guess, is going to be 3s. So it's 2s square plus 6s plus 4. This becomes 3s plus 3. And it's still not equal. Alright, just a second, let's see what's wrong. Okay, so there is one term missing here then. Plus 2s. Okay, so now this is 7 and this is 1. So now you have the correct expression, this. So you can observe that this part is a strictly proper rational function, so or a transfer function. And you have decomposed the transfer function into two parts, and the second part is now strictly proper. So now let's look at case 3, where Fs has distinct poles. Okay, so that was case 1. It involves multiple poles. At the same location. Alright, so let's take an example. This is going to be Fs equals s square plus 2s plus 3 over s plus 1 cube. So this is strictly proper, but has multiple poles or eigenvalues at s equals to minus 1. So the way to get the partial fraction expansion for this is you have c1 over s plus 1 cube yeah. So if there are 3 repeated poles or eigenvalues at s equals minus 1, you will have constant c1, c2, c3 associated with s equals minus 1. And so to find out what c1, c2, c3 are, what you can do is just equate these two equations. And equate the coefficients of similar powers, same power. So let's see. This is going to be c plus c2 times s plus 1 plus C3 times S plus 1 cube, and this is going to be equal to S square plus 2S plus 3. So you can expand this and then just compute same parts of S. Alright, so now let's move on to the next part. So partial fraction expansion is going to be used in the Jordan normal form and the diagonal form. But before this, let's recall the controllable canonical form and the observable canonical form. So controllable canonical form CCF and the observable canonical form OCF. Alright, so I'm just going to write down the general expression. We have already covered this in the last week tutorial. So you have, for example, for an nth order system, we have x1 dot, x2 dot up to xn dot, and then we have a chain of integrators. So we have x1, x2 up to xn plus b times u. So let's now fill the entries. So it's going to be 0, 1, 0 throughout, 0, 0, 1. So this actually goes on, and here this has a second last row, and the last row is this minus an minus 1 all up to minus a1. So I'll just write down what the transfer function is. Just 1 second. Yeah, the general transfer function that we are considering here is ys over rs equals to some n degree polynomial in the numerator. So it's b1 sn minus 1 all up to over a is not s to the power n, a1 s to the power n minus 1 up to a n minus 1 s plus, sorry, an. Alright, so then this is clear. This is the controllable canonical form, like this as a and b. Alright, and this is for the case when we do have something in the numerator. So for this case, we have some C matrix. And what would that be? So let's just say that this is the vector x plus some d times u. So let's write down what C is. So this is going to be bn minus b0 times an. So you're going to go from here. Then we have bn minus 1 minus v0 an minus 1. And the last entry is going to be b1 minus b0 times a1. And the coupling with the input would be given by this coefficient. So this and this are the CCF forms. And we saw in the last lecture how to obtain the OCF form from the CCF form. Alright, so this is clear. Let's solve a question. Okay, so let's consider this following system. We have 3s cubed plus 6s squared plus 5s plus 7 over s cubed plus 6s squared plus 15s plus 11. Okay, so observe that this is a proper transfer function. And let's see that we have been given state space representation. So 3 by 3 matrix, 0 1 0, then we have 0 0 1, minus 11 minus 15 minus 6 because of these coefficients, times x plus b times u, and y is given as some constant times x plus 3 times u. So 3 because this is the coefficient of the highest part, and then you have a, b, c. So the question is find the values of a, b, and c. So we have just seen the general formula. Let's apply. So a is going to be, let's see, it's going to be 7 minus 3 times 11. Then we would have 5 minus 3 times 15, and c is going to be 6 minus 3 times 6. So 7 minus 33, 5 minus 45, and 6 minus 36. And this is going to be minus 26. Alright, so I hope this question was clear to everyone. And now let's move on to the next forms. The Jordan canonical form. Okay, so in these forms, the main interest in the matrix is this diagonal line. So we'll have the eigenvalues or the poles of the transfer function along the main diagonal, and then zeros everywhere if we have distinct poles. And this canonical form follows directly from the partial fraction expansion of GS. Alright, so let's first look at the diagonal form. So we have the diagonal canonical form, and we have distinct eigenvalues. Okay, so let's consider again a general form of the transfer function. Let's write this down. So we have n minus 1 up to bn minus 1 s plus bn. We have an nth order system, and then we have poles. So instead of writing the general form of the denominator, which we have seen earlier, I am going to write this as a product. So it's formed by the poles or the eigenvalues of the transfer function. So if we have n distinct eigenvalues, this is how the denominator would be written. Okay, so just observe that this is proper, because it might be that V0 is not 0. Okay, so if this is the case, we can write this as V0 plus C1 over S plus 1 P1 all over till C and S plus Pn. Okay, So you have seen how to derive this expression in this week's lecture. Now let's write this down in the state space form. So you can find out what C1, C2 up to Cn are. We have just seen this. Now if you know what C1, C2 and Cn are, you can form this matrix. So we would have minus P1 minus P2 minus Pn along the main diagonal, zeros everywhere else. This is x plus 1, 1 or up to 1 times u. So the control appears in the differential equation of each of the states, all the n states. And then we have the output y, which is just a linear combination of all of the states. This is x plus v0 times u. So this is 0 for a strictly proper transfer function. Alright. Then let's just recall the Jordan canonical form before we get to some questions. Okay. Now for Jordan canonical form, the difference from the diagonal form is that we can consider multiple eigenvalues at the same location. So this is for multiple eigenvalues at the same location. So let's see what the general form of the transfer function is. The numerator remains the same. So an nth degree polynomial. So let's say there are, for example, 3 repeated eigenvalues at P1. Then we have S plus P2 all up to S plus Pn. Okay. So we have seen how to expand this using partial fraction expansion. So let's see P0. If it's not 0, then we would have C1 upon S plus P1Q plus another C2. So let's just write C12 and C13. So this is for the first eigenvalue plus C2 upon S plus P2 all up to Cn upon S plus Pn. Okay, so if you have written it right down like this, x1 would be, sorry, x dot would be, okay, so the first pole is P1 and it's a repeated pole. So let's just write down the Jordan block for this. Minus P1 and 0. Then you would have 0 minus P1 1. So you can observe that this is just shifting to the right. And then because it has 3 repeated poles, it would have been a size of 3 by 3. So I'm going to actually write this down in a dotted form. This is a Jordan block for P1. Then you have 0, 0, 0 and alright, so rest of the poles are just distinct. So you can start from the main diagonal. So this is the main diagonal of the matrix. You have zeros, zeros, and along the main diagonal, you'll have the next distinct pole, then minus P3 all up to minus Pn. Okay, so Let me just say that this is the A matrix. B is just a column vectors of 1. C is for a linear combination of all of the states. Okay, so C1, 1, then C1, 2, C, sorry. I'm going to write down all up to Cn. And then D is going to be B0 because of the coupling between input and output from here. Okay, so let's look at a simple example. Let's say that we have a feedback system which has a closed loop transfer function. It's going to be ys over r of s on s plus 1 and s plus 3. So the question is obtain the diagonal canonical form of the above system. Okay, so let's observe two things. That first, it's a strictly proper transfer function. So I'm just going to write it as TF, and it has distinct eigenvalues. So we have a simple case here, and let's just write down what the matrices are. Okay, so let's first write down the partial fraction expansion. We have C1 over S plus some C2 over S plus 1 plus C3 over S plus 3. Alright, just a second. Yeah, this is going to be 10 times S plus 4, S plus 1 and S plus 3. So we have just seen how to compute these coefficients. So we have C1 is going to be computed at S equals 0. So this is 40 over 3. C2 is going to be 10 times S plus 4 upon S plus 3 evaluated at S equals minus 1. So this is going to be 3 and then 2. Now let's compute the last constant. We have C3 equals S plus 1 evaluated at S equals minus 3. So this is going to be just 1 minus 3 times minus 2. So we have plus 5 over 3. Okay, so now we know what the partial fraction expansion looks like. Let me just write that down. Ys over rs is going to be 40 over 3. So this is going to be minus 15 upon s plus 1 minus 5 s plus 3. Okay, now let's take rs to the right hand side. We get so let's write minus 15 s plus 1 times rs. Okay, rs. Okay, So what we're going to do is consider this as x1 of s, this as x2 of s. This is just to illustrate how we get the diagonal form x3 of s. This is rs over s. Take the inverse Laplace transform and we get x1 dot equals u. Okay, then the next relation is x2s equals rs upon s plus 1. Okay, this implies that x2 can be like this, and from the inverse Laplace transform we have x2 dot plus x2 equals, okay, so this is going to be u, so let's just write down as u of t. So x2 dot is minus x2 plus u. Now we have the last state, so we have x3 of s equals rs over s plus 3. This implies that, so this is 3 times x3 of s rs, and then we have the inverse Laplace transform. This gives us x3 dot equals minus 3x3 plus u. So now we have x1 dot, x2 dot, x3 dot. We have the relation between x1, x2, x3 and u. So let's write this down. Zeros all throughout times 1. So this is true because u appears in all the equations. And we have 0, minus 1, 0. And the last one is 0, 0, minus 3. So you know how to get that, right? If we just use the direct form, we have the pole at 0, pole at minus 1 and a pole at minus 3. Alright. And we also have this y. So it's a linear combination of x1, x2 and x3 plus, let's see, we have a strictly proper transfer function. So it would be 0 times u. And we already know what C1, C2 and C3 are. So I'm just going to write them down. 40 by 3. Then it's minus 15 and plus 5 by 3. So this is the diagonal canonical form. Alright. Now let's look at some other example. Okay. So we have a transfer function again. Y is over u of s equals s plus 3 over s square plus 3s plus 2. So obtain the diagonal form. So let's see first that it's a strictly proper transfer function. And to see if it has distinct eigenvalues, Let's look at the roots of the denominator. So let's check. Minus is 0. So this is 1. And alright, so s plus 1, and then the other one is 2. Alright, so we have ys over us equals s plus 3 upon s plus 1, s plus 2. Okay, so we have distinct eigenvalues at s equals minus 1 and minus 2. So we can obtain the diagonal form, and we have c2 over s plus 2. So let's quickly find out these coefficients. So c1 is s plus 3 over s plus 2 at s equals minus 1. This is s2, and evaluated at s equals minus 2. So we have minus 1. Now this can be written as 2 over s plus 1 minus 1 over s plus 2. So you know what C1, C2 are? Let's form the A matrix. It's a second order system. So just two eigenvalues along the diagonal. B for the diagonal form is already a vector of ones, a column vector. C is these constants, 2 and minus 1. And D is 0 since it's a strictly proper transfer function. Okay, so this was a simple example. Now let's try a higher order system. Okay, so there's a transfer function g of s. This is s plus 3 s cube plus 9s square plus 24s plus 20. Okay, so the question is again find the diagonal form. Okay. So I hope you can hear me. If not, then just let me know. Alright. Okay, so find the diagonal form. So we will have to find the roots of the denominator polynomial. So let's see. So first this is strictly proper, and then we'll have to find out the roots. So where's okay. So let's check. S equals minus 1. So it would be minus 1 plus 9 minus 24 plus 20. So this is okay. Now let's check minus 2. This is minus 8. Then it's 36. Then it is 48 plus 20. So we have 56 and this is 50. Alright, so we have S equals minus 2 as one of the roots. So let's find out what the other is. I'm going to do this on the side. So let's see. S square, and we have s cubed plus 2s squared. We have 7s squared plus 24s plus 20. We have 7 and 7 squared plus is this correct? Okay, sorry about this. We have 14s, and we have 10s plus 20. So just 10. Okay, so we have s plus 2 times s square plus 7s plus 10. Okay, so now the roots are, let's see. Minus 1 is not a root, not minus 2. So it's 16. Okay, so we have s plus 2 and s plus 5. Okay, so there's 2 b. Okay, so it's also s plus 2. We have gs as s plus 3 over s plus 2 squared s plus 5. So what we can find out is actually the Jordan normal form. Okay, so for that we do need the partial fraction expansion. We have c1 over s plus 2 squared. Okay, then we have c11, c12, s plus 2, and then c2, s plus 5. Okay, so this is going to be s plus 3, s plus 2 squared, s plus 5. Now let's expand both sides. This is going to be s plus 5 plus c12 s plus 5 times s plus 2 plus c2 times s plus 2 squared equals s plus 3. So let's see, s times, what we can do is just expand this first. You already know what this is, so that's s square plus 7s plus 10 plus c2 s plus, okay, so we have s square plus 4s plus 4. Okay, so let's Scrub the square terms together. We have C12 plus C2 plus S. We have C11 plus 7 times C12 plus 4 times C2. Then we have 5 times C11 plus 10 times C12 plus 4 times C2 equals S plus 3. So when comparing the coefficients, so what do we get? We have that C12 plus C2 equals 0. Then we have C11. So let's do this. We substitute C12 directly. Minus S7C2 plus 4C2. It is going to be 1. So we have C11 minus 3C2 equals 1. So this is one of the equations, and then we have 5C11 minus 10C2 plus 4C2 equals 3. So this implies we have okay. So let's say this is A and this is B. So 5 times A becomes 5C11 minus 15C2 equals 5. So let's compute. We have minus 9 C2 and 2. C2 is going to be minus 2 over 9. Let's see, and then C. This implies that C12 is going to be plus 2 by 9. So all we need to find out is C11 now. C11 is 1 plus 3C2. This is 1 minus 02 by 9. Okay. So we have 1 minus 2 by 3, which is 1 by 3. Okay. Now we have the partial fraction expansion. Let's go up. 1 by 3 upon s plus 2 square plus 2 by 9 s plus 2 is minus 2 over 9 s plus 5. Okay, so now we form the Jordan block. So we have the matrix A. So it's going to be a 3 by 3 matrix. So let's see. For the last eigenvalue, it's just going to be minus 5. We need a 2 by 2 Jordan block. I'm going to expand this a little bit. And 0 and 0. So this is going to be minus 2, 1, and then 0, minus 2. Because there are two repeated eigenvalues at minus 2. Then we'll have again the B vector 1, 1, 1. And C is going to be, let's just write down 1 by 3, 2 by 9, minus 2 by 9. And D is 0, because we just saw, I think in the introduction, yeah, it's strictly proper. Okay. So I hope this question was clear to you. Now let's move on. So let's write this down as a question. Okay. So state space models, what I mean is the canonical forms, the diagonal canonical forms. So let's look at the first example. Sorry, first question. We see it's just a second. Okay. So we have GS, and then we have repeated poles at the first for the first eigenvalue. We have 5 over s plus 1 squared s plus 2. Alright. So one thing is that it is strictly proper. So we know what the D matrix is going to be. There is no coupling between the input and output. And now we need to find out what the coefficients are. So we have the partial fraction expansion. Okay, then we have 5 over s plus 1 squared s plus 2. So now let's simplify this. We have C11 times s plus 2 plus C12 times s plus 1 and s plus 2. We have C2 times s plus 1 squared. This is just 5. Alright, so let's expand them first. So this is going to be s square plus 3s plus 2 plus c2 times s squared plus, okay, so this is 1, 2s plus 1 equals 5. Now let's club terms for each power of s. We have s squared c12 plus c2 plus s times, just a second, okay, so I hope you can still hear me. So it's s times c11 plus 3 times c12 plus 2 times c2, and then for the constants we would have 2c11 plus 2c12 plus c2. Now let's just compare the coefficients. So the first one is clear, c12 equals minus c2. Okay, and we'll just substitute c12 in the rest of the two equations. So we have c11 minus 3c2 plus 2c2. This is c11 minus c2 equals 0. And then the last equation, minus 2c2 plus 2c2. This is 2c11 minus c2 equals 5. Okay. So let's subtract them. And if this is true, then from 2 you have c11 equals c2 equals 5. And from the first equation, we have c12 equals minus 5. Okay. So we have the coefficients. That's from the matrices. So this is a second order system, a 2 by 2 matrix. Sorry, it's third order. It's 3 by 3 matrix. The last row is for the distinct eigenvalue at -2. We will have a 2 by 2 Jordan block and then 0. So the repeated eigenvalue is at -1. So -1, 1, and you shift this by right, so you have 0 and -1. So this is the Jordan block for lambda equals -1. Then we have the B vector 1, 1, 1. We have already computed the coefficient, so C is going to be 5 minus 5, 5, and there is no coupling between input and output, so this is 0. Okay. Now let's look at a case when we do have coupling. So this is B. So G of S is S cube plus 8s squared plus 17s plus 8 upon S plus 1, S plus 2 and S plus 3. Alright, so let's observe some things first. This is just a proper transfer function. And it has distinct eigenvalues. Alright, so if it has distinct eigenvalues, so this is very easy to form. It will be -1, -2, -3, 0, 0, and then the rest of them would be 0. E is going to be a 3 by 1 column vector, and D is going to be 1, which is the coefficient of the highest power of S, S cubed in the numerator. And now we just need to find out what C is. Okay, so for C we need the partial fraction expansion, so let's write that down. G of S is C1 upon S plus 1 plus C2 upon S plus 2 plus C3 upon S plus 3. So C1 is going to be S cube plus 8s squared plus 17s plus 8, and you remove the term for the eigenvalue, corresponding eigenvalue, and you have to compute this at S equals -1. This becomes -1 plus 8 minus 17 plus 8 over, sorry, it is going to be just 2. So we have this is going to be -1. And we have C2. C2 is going to be S cube plus 8s squared plus 17s plus 8 over. So remove the term for the corresponding eigenvalue. We have S plus 1, S plus 3, and this ratio evaluated at -2. Alright, so we have -8 plus 32. Okay, so -34 plus 8 upon -1 and just 1. Okay, so this cancels out. We just have plus 2. Next we have the last constant C3. Okay, so let's do this. S cube plus 8s square plus 17s plus 8 over s plus 1 and s plus 2 minus 27. Then we have minus 2 and minus 1. So let's check this once. This is okay. Alright. So let's just compute this. 27 and 51. That's easy. So I'm just going to write this down. Minus 78 plus 72 plus 8. Okay. So these were distinct eigenvalues. We got C1, C2 and C3. So C is going to be minus 1, 2 and 1. Alright. And since it was a strictly proper transfer function, we got D equals 1. Now let's move on to another example. So it's a question. The transfer function is given like this. So g of s is 50 times 1 plus s over 5 s 1 plus s by 2 and then 1 plus s by 50. Okay, so let me check once. Alright. So let's get to the standard form for the transfer function. We have 50 times s plus 5 over 5. Then we have s. We have s plus 2 by 2. So GSS and s plus 2 s plus 50 and this times 100. So this is 1000 times s plus 5, s times s plus 2, s plus 50. Okay, so this is strictly proper. And this has distinct eigenvalues. So we already know what the A matrix is going to be. 0, minus 2 and minus 50. Zeros everywhere else. B is going to be a column vector of 1s and D is going to be 0. We need to find out what C is. Okay, so let's quickly perform the partial fraction expansion. We have GS equals C1 over S plus C2 upon S plus 2 plus C3 upon S plus 50. So C1 is just the transfer function except the eigenvalue at 0 evaluated at 0. I think that's it. Yeah. So this is just 50. C2 is going to be over S plus 50 evaluated at -2. So this is going to be, sorry, just calculate. Okay, let me check. Yes, so this is just, let's put a minus sign here. And you can simplify this further. Yes, I'll be sharing the notes. So you can just simplify this and you'll get the C matrix, C vector as, okay, so you already have C3 also. This is B S plus 5, S and S plus 2 evaluated at S equals -50. So this is going to be, and then you can also simplify this. You get this as 50, the value of C2 and the value of C3. Okay, so I hope this was clear to you. Let's look at now differential equations. Okay, so again by this I mean the diagonal form or the Jordan one, whichever is applicable. Alright, so let's start with the easy case. We have the third order derivative of y plus the second order derivative plus 11y dot plus 6y equals u. Okay, so let's take the Laplace transform. Get s cube ys the 6s square ys plus 11s y plus 6y equals u. Here we have ys over us equals 1 upon. So we have s cube plus 6s square plus 11s plus 6. Okay. So this is a strictly proper transfer function. and this implies that D is going to be 0. We already know what B is going to be, so it's a third order system, 1, 1 and 1. We now need to find out what the matrices A and C are. Okay, so for that we first need to decompose this. We need to find the eigenvalues. So let's check. Does S equals minus 1 satisfy this? So it's going to be minus 1 and plus 6 minus 11 and then plus 6. Okay, so this is fine. We have S plus 1 as one of the roots. So let's find the other two. So we have S cubed plus S squared. And we have 5S squared plus 11S plus 6. This is going to be 5S squared plus 5S. Okay. So we have the denominator as S plus 1, S squared plus 5S plus 6. Okay, now let's look at the roots of this equation. So at minus 1, we would have 1 minus 5 plus 6, so not 0. Let's see at S minus 2. So we would have 4, then minus 10 plus 6, which is correct. Okay, so we'll run more. So let's see. Have 3s plus 6, and this is just 3. Alright. So finally we have s plus 1, s plus 2, and s plus 3. Okay, so these are distinct eigenvalues. These imply that A is going to be minus 1, minus 2, minus 3 along the main diagonal, and then zeros. Okay, so now let's quickly perform the partial fraction expansion. So we have 1 over s plus 1, s plus 2, s plus 3 equals c1 upon s plus 1, c2 upon s plus 2, plus c3 upon s plus 3. So c1 is just 1 upon s plus 2, s plus 3. I will get this. So we have just half. c2 is going to be, I'm going to compute this directly at minus 2. So minus 1 and 1. And c3 is going to be evaluated at minus 3. So minus 2 and minus 1, this becomes half. Sorry, this is minus 1. So c becomes half minus 1 and half. So we have C, A, and we have already computed what B is, and D. Alright. So now let's look at some more examples of differential equations. This was the first one. Alright. So we have a third order system again. So then it's double dot plus 2y dot equals u dot plus u. Okay. So let's take the Laplace transform of both the sides. We have s cubed ys plus 3 square y plus 2 sys equals sus plus us. So this implies that ys over us is s plus 1 upon s cubed plus 3s squared plus 2s. Alright, so let's get this down to the general form. We have s common, s squared plus 3s plus 2. Okay, so what are the roots? Okay, so s equals minus 1 satisfies this, and s equals minus 2 is 4 plus 2 1. Alright, so this also satisfies. So we have s plus 2. So this is easy since this is a strictly proper transfer function, and this also has distinct eigenvalues. So we already know what the three of them are going to be is 0, minus 1, minus 2. B is going to be 1, 1, 1. D is 0. So the main thing in the Jordan normal form and the diagonal form is to find out what C is. So let's compute. We have this transfer function as C1 over S plus C2 upon S plus 1 plus C3 upon S plus 2. C1 is going to be, I'm going to compute this directly now. So this transfer function at S equals 0. So 1, 1 and 2. Then we have C2 at minus 1. Okay, so there is actually a cancellation here. So there are actually just this can be reduced to a second order system. So what we can write this down as okay, so this doesn't exist, and this is actually C2. So let's just check this once. We have, okay, so this is fine. This is alright. Okay. So you can see that even though we had the third order differential equation, we're going to reduce this to a second order state space model. So let's see what C2 is then. C2 is just, okay, so it's going to be 1 upon S at S equals minus 2. This is minus half, and this is half. So C is going to be half minus half. D is 0. B is now just 1, 1. And we have A as 0 minus 2, 0, 0. Okay, so I hope this was clear to you. So now let's do one more question of a differential equation. So it's again third order. So you can observe that there is the third order derivative of u, and we have a third order system. So b0 is going to be 1, and we'll see that it's a proper transfer function, not strictly proper. So let's just take the Laplace transform. So just write this down as US. Okay, so you can observe that this LHS of the differential equation is the same as that we have in 1. So let's see if this is true. Third order derivative 1, 6, 11, and 6. So this is true. So I'll just write down the partial fraction expansion there. Directly from the first part. So we have s plus 1, s plus 2, and s plus 3. So this is just a proper transfer function, and it has distinct eigenvalues. Okay, so we already know what a is going to be. Minus 1, minus 2, and minus 3. B is just 1, 1, and 1. D is 1. And now let's see what C has to. Okay, so G of S, which is just this. So let's quickly find them out. C1 would be minus 1 plus 8 minus 17 over. This is now C2 would be minus 8 plus 32. Then it would be 4 plus 8 over minus 1 and 1. So I have minus 2 over minus 1. And then finally LC3 evaluated at -3. So minus 27 plus 72, then okay, over -2 and -1. Sorry, so let's see. We have 80 and then we have minus upon -2. Sorry, so it becomes plus. So this is just 1. So C is therefore -1, 2 and 1. Alright, so we already have the A, B and D matrices. Alright, so apart from this, if you have any doubts from the assignment, ask me now. Okay, so if not, let's just do a quick last questions and then we'll end for today. Alright, so the transfer function is already given. It's 2s squared plus 6s plus 5. And the denominator is already given in simplified form. So this is it. So we have just a proper transfer function. And we have repeated eigenvalues. So let's just check if the denominator does not have the same zeros as the poles. So at -1, the numerator is 2 minus s plus 5. This is also nice. Alright. So since these are repeated eigenvalues for a third order system, we already know what A matrix is going to be. So this is going to be 0, 0, 2. And you need a 2 by 2 Jordan block. -1, 1, and then shift this, so this becomes 0, -1. We know what B is, and okay, so this was strictly proper. A is going to be 0. So now our job is just to find out what C is. So let's quickly find the partial fraction expansion. This is going to be 2s squared plus 6s plus 5 over S plus 1 squared S plus 2. So we have expanded both sides. Now we have again S squared plus 3S plus 2. Now let's combine the terms. So for S square, we have C12 plus C2 again. For S, we have C11 plus 3C12 plus 2C2 plus 2C11 plus 2C12 plus C2. Okay, so C1 plus C2 equals 0. I have seen this before. For this, we have, alright, this is not the case this time. We have C1 plus C2 equals 2. So we have C12 equals 2 minus C2. This is different from the previous cases of repeated eigenvalues. Then we have C1 plus 3 times 2 minus C2 plus 2C2. So we have C11 and we have minus C2. This implies C11 equals C2. So we have 1, 2 and the last equation, which is 2C11 plus 2C12 plus C2 equals 5. Alright, so let's substitute for C11 and C12. So this is going to be 2C2 plus 2 minus C2 plus C2 equals 5. So I have 2C2 plus 4 minus 2C2. So this implies that C2 is just 1. So C11 is 1 and C12 is 1 again. So this is just row vector of 1. So let's see, we have C here. We have already computed A. Because of repeated eigenvalues, we have B, and then D equals 0 because it's strictly proper. Alright, so if we, just a second. Okay. So if you don't have any doubts, we can end for today. That's fine. Alright, thank you.